Postman Pat, Postman Pat, Postman Pat, and his black and white cat. Early in the morning, just as day is dawning, he picks up all the post bags in his van.
It's holiday time, Jess. Nothing can disturb us now.
Mrs. Thornberry said you forgot to deliver her parcel. You have to go find it.
I'm sorry, Mr. Quinn. Let's sort this out.
Hi, this is the Econometrics Department, Mrs. Thornberry speaking.
Hi, it's Pat here. Could you describe your missing letter?
Thanks, Pat. I was expecting a parcel sent by a client. It's a piece of regression analysis. Regression analysis is a method of describing the linear relationship between a given variable and one or more other variables. In this case, you are looking for a letter that shows the relationship between two variables. The first variable, x, is deterministic. It is independent and assumed to be controllable. We treat the second variable, y, differently, Pat. It is dependent and stochastic. It is random and will follow a probability density function. Can you, or just picture it yet?
I'm picturing a scatter graph, with a line of best fit.
Exactly, Pat. Regression analysis develops a relationship that allows the user to forecast how a change in variable x will affect y. Correlation in comparison is a lesser measure than regression, as it assumes that x and y are symmetrical variables. Future changes are averaged based on the correlation coefficient. My client is coming in to look at improving his work. Hopefully you can deliver the letter by then.
So Postman Pat and Just the Cat went on an adventure to look at the regression analysis based on what Mrs. Thornberry had said. And eventually they found it.
I am Yusufun. I trust that you have received my letter asking for your help with regression analysis.
Thankfully our postman delivered it just in time. Let's have a look at your problem. You have researched how the number of flowers you send your girlfriend affects her happiness. However, as a girl's happiness is very unpredictable, we see random disturbance. This is caused by measurement error, unobservable experiments, and random influences that can't be modeled.
So how can I improve my forecasting?
The rough line you made by eyeballing the data is fixed. It follows the standard time-dependent equation for a straight line. But to allow for random disturbance, we need to add another term, ut.
How do I calculate ut?
We use the ordinary least squares estimator. As you can see, we want to determine how far our observations lie from the line. By measuring the distance between our observed value, y, and our estimated value, y hat, we are able to calculate the residual for this particular observation, u hat. We must square this to ensure all values are positive. We repeat this for the other observations. This allows us to calculate the residual sum of squares, or loss function.
What's next?
We want to minimize the distances to ensure a best fit. We expand the loss function like so. Using this, we differentiate with respect to our estimators for alpha and beta, and set the first derivative equal to 0 and solve, giving the following equations. These new parameters allow us to revise the line of best fit, to give more accurate projection.
But is it really that good?
Well, that depends if these assumptions hold. 1. The errors have a mean of 0. 2. The variance of errors is constant and finite. 3. The errors are independent. 4. There is no relationship between errors and their x variables. If this is the case, we can say that it is the best linear, unbiased estimator. OLS will also exhibit 3 desirable estimator properties: consistency, unbiasedness and efficiency. Furthermore, you can precisely measure the estimator's accuracy against the sample by calculating standard error.
Great, now I can forecast how many flowers to send my sweet Olivia. Pat, would you do the honor and deliver them?
And of course, Pat and Jess delivered the flowers and saved the day.
Pat feels he's a really happy man.